Chalk. It's the white powdery stuff that gives rock climbers, weightlifters, and gymnasts an advantage in their grip strength during their sport. And it's also very similar to a commonly used chemical in organic chemistry labs. So OChem students, you might want to stick around too. But how and why does it do its job so well? Well, let's get into the chemistry of chalk. Okay, so when I say chalk, what I'm actually talking about is something called performance chalk, which is chemically different than the chalk you'd use on a blackboard in a classroom or on the sidewalks in the street when you were a kid. That kind of writing chalk is something called calcium carbonate, which is incredibly water soluble. So whenever it rains, all your sidewalk art goes away. Whereas performance chalk is made of something called magnesium carbonate, which is incredibly water insoluble. So that's why athletes will be putting it on their hands, and it takes a lot more sweat and water for it to wash away than regular chalk does. But we're still not at the chemical level of it yet. Let's go another step deeper to figure out why and how it relates to organic chemistry. Okay, so before we go any further, I want to explain why we can even talk about chalk in the framework of organic chemistry. Chalk isn't an organic substance, so why do we care about it? Well, when you're in an OChem lab and you make something and it has some amount of water in it as an impurity and you want to remove that without heat or anything like that, you add a drying agent to it. A really common drying agent is something called magnesium sulfate, which is very similar to magnesium carbonate or climbing chalk. They're both from this family of chemicals called hydrates. A hydrate is an ionic compound with a crystalline structure that can trap water. What's important is the word trap. The water isn't bonding like I mentioned before. In fact, you can think about it like magnets. So I have two magnets here from a calendar, and if you hold them close together, they start to pull each other. And if I was to let one go, it becomes attached to it. What's important to note is that these two are not bound together forever now. They're not one object. They're not fused or melted together. If you put in just a little bit of energy, it comes apart. It's just trapped there. That's strikingly similar to how our hydrates are going to work. But let's go investigate that on the molecular level. I find one of the most helpful ways to understand chemistry and really all of science is visualization. So let's do that with the chemistry of chalk for a moment. Here we have water, H2O. And here we have magnesium carbonate, MgCO3. Let's take a look at water for a moment. So water here is made up of HOH, as I stated. But you would think that because it's HOH, it would just be a straight line. A lot of 3-atom molecules are like that. But water is interesting. It's this bent shape with a 104.5 degree bond angle. Why is that? Well, oxygen is a pretty big atom relative to hydrogen, and it also is incredibly electronegative, the second most electronegative element on the periodic table, in fact. Well, electronegative is the natural affinity for something to pull electrons to want to take them. So water here is taking up more of the electron's time and rotation around all of the different atoms here. So it forces the bonds to be compressed and bent into this angle. And why that's important is that it creates a slight negative charge around the oxygen and a slight positive charge around the hydrogens. And so it has this thing called a dipole. It's electrically balanced overall. Water doesn't have a charge, but internally there is a difference in the charges on a very small scale. But that influences a lot of things like its attraction to things. So let's keep that in mind for a moment. And here, with magnesium carbonate, climbing chalk, let's talk about this for a moment. It forms a crystalline structure like table salt sodium chloride, and that forms a lattice structure because there's a repeating pattern inside of that structure. And here in magnesium carbonate, you're actually going to notice that there's no bond between the magnesium and the carbonate. What you're going to notice here is that the carbonate here stole 2 electrons from the magnesium. So the magnesium has a +2 charge, Well, the carbonate has a -2 charge, and this attraction, because of their opposite charges, is why they're kind of stuck together without a bond. And that's why it forms one ubiquitous material that we call chalk, or magnesium carbonate. So, when water is approaching magnesium carbonate, water has that negatively charged dipole on the oxygen, while magnesium is positively charged, and so they come together and are attracted to each other and snap together, just like the magnets from earlier. They're not bonded, they're not sharing electrons or taking electrons, they're just in this push and pull of attraction. If you input a little bit of energy, say heat, the water goes away. But without that, they stay together. But earlier, we mentioned that magnesium sulfate in organic chemistry labs and magnesium carbonate, climbing chalk, can absorb way more water than just one molecule for every one molecule of chalk. Magnesium sulfate can grab up to 7 waters, and magnesium carbonate can grab up to 5 waters. How is it grabbing that many? The answer's pretty cool. So there's this concept called molecular geometry. It's a way of labeling how many possible interactive sites there are on elements and molecules. Well, magnesium here is octahedral. It can have up to 6 possible points of interaction. Here, 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 and here, on all those different directions of the axes. So those are all the points where magnesium can interact with other things. Carbonate takes up one of those spots in magnesium carbonate, for instance. That takes up one of the 6. There are 5 remaining. And magnesium carbonate can hold up to 5 waters. So waters will come in and fill out the rest of those 5 spots. And that is how you get a hydrated magnesium carbonate. But what's even more impressive is that's on the scale of 1 magnesium carbonate. In a chalk bucket like the one I showed earlier, there's a bunch of chalk. So if we expand this out, we see that a few molecules of chalk can absorb a huge amount of water. And that is why chalk is so good at absorbing water on your hands and sweat. And that's why athletes are using it to get a better grip. Thank you guys so much for watching. I really appreciate it. Please let me know if this information was helpful for anything at all. I have a lot of ideas for videos I want to make, but if you have any scientific concepts or ideas, whether it's academic or something from pop culture, please let me know, of course, and I would be happy to talk about it and kind of go into depth on it. All of my resources I used to make this video are in the description down below, so if you have any questions, check those out or leave me a question. I'd be happy to go over more of this with you in detail. I also want to give a special shout out to Kyle Hill from the facility, one of the best science communicators on the internet in my opinion. He helped me kind of structure this video, and I wanted to make sure that I credit him properly with that. So thank you very much, Kyle. Check his stuff out. Links in the description down below. And finally, if you like this video, consider liking it and maybe even subscribing. It's not too much of a big deal for you, and it matters a lot to me, so thank you very much. Have a good one, guys.